talk about what is a data-intensive applications. So how each of you, maybe you have different definition, defined data-intensive application and have this definition change from the first edition to the second edition. And maybe Chris, maybe you can start.
Oh boy.
Sorry for dumping it on you. Yeah, Go ahead.
No, it's fine. I think for me, data-intensive application is an application in which data is central to the value it provides. So, a classic example of this would be something like a search engine or, analytics software, things like that. And I think what we find these days is data is central to almost every application's value proposition. So for me, I think it ends up being like nearly all systems end up being data-intensive applications. I think if you drill down a little bit, we often talk about like application engineers, where what we really mean are like mid-tier and back-end engineers. And I think even there, at the microservice or web service level, the same kind of rule applies, where if data is central to the service you're providing, it's probably a data-intensive application. And it turns out, probably why this book has resonated so much is it turns out almost everything is a data-intensive application. So that's my definition of it, is where the data is really central to the value proposition.
Yeah, for me, I would add that it's, I think where the data is a primary challenge of the engineering behind the application as well. If you have a really small amount of data, you can keep it in a spreadsheet and that's done. And it might be very, very valuable data, but in that case, the data is not a huge challenge. But if like the volume of the data is large, if it's very fast changing, or if it's like a really complex data model, in those cases, then data becomes a primary challenge. And that's the sort of type of app that we're thinking about here.
Okay, thanks. And did the threshold of what you consider data intensive change from the first to the second edition? For I don't know, maybe in the first edition it was a megabyte, now it's a petabyte, or whatever, or the definitions are different.
That's a good question.
It's changed hugely.
Yeah, I think in my mind, at least, to Martin's point, it's really a question of when it becomes a challenge. So you can have, depending on the query processing you're doing and the data you're dealing with, a relatively small amount of actual data can be a really big problem to process, or you can have a very large amount of data that's actually pretty straightforward to process. I think in combination with that, the individual machines we have now have gotten really astronomically large. And so you can do a lot more on a single node. That doesn't necessarily mean it's not data intensive. Even on a single node. We spent a whole bunch of time in the book talking about storage engines and encoding and stuff like that. So I think it's a little tricky to answer that.
Okay, thanks. What are the main differences between the first edition and the second edition? And maybe we can split it to parts, because it's a huge question and a huge book, a large book. So let's start with which topic from the first edition become less relevant in the second edition. Did you decide to remove something which is no longer as relevant?
A few things we've removed or deprioritized, MapReduce being one example. So that's something that we spent quite a lot of space on in the first edition, and which just has become largely obsolete. It's still relevant as a teaching tool in order how to think about how you might run joins over very large data sets, for example. But we've reduced the amount of coverage of that in the second edition.
Okay, and the second part of it, I guess, which part did you emphasize or even add to the second edition that was not there in the first edition?
Yeah, I'd say there are probably two main parts. So one is the rise of cloud-native architecture. So that is where people are not just building things based on local computational resources, like the disk attached to a single machine, but people building services upon services. And that's something, of course, that it already existed 10 years ago, and in principle, is somewhat reflected in the first edition. But in the last decade, that has actually had quite a big impact on the architecture of data systems as they are designed. One example of this being people building databases where the underlying storage is an object store rather than a local disk. And that actually changes the model on quite a fundamental level. And so that's an idea that we wanted to incorporate throughout the book, because it affects lots of little different decisions in different places. So it's not like a new chapter on that, but rather an idea that we've weaved in throughout the book. And then the other big thing that has changed is AI, obviously. We decided not to make this a book about AI per se. I think there are probably better books that are focused just on this. So it's still a book on data systems architecture, but there are various ways in which the need to support AI systems has affected the types of things people are doing. Partly this is in using batch processing to prepare large training data sets, but it's also in data modeling, for example, where people are using data frames increasingly as a data model. It applies to storage engines where people are using vector databases to do like semantic similarity search. And so all of these things are in support of AI, and these things we've then incorporated into the appropriate places in the book. So like there's now data frames coverage in the data models chapter. There's now vector indexes coverage in the storage engines chapter, etc.
Okay, thanks. And Chris, maybe it's a good question for you, because I know that you are very much involved in databases on top of object store with ScyllaDB. So maybe you can define or explain what is cloud native for you. And the reason that I'm asking that I'm seeing people like using this term in many different ways. Cloud native is running on EC2, or is cloud native? What's your definition of it?
Oh boy, I saw that question on the list, and I there is no good answer to this. To be honest, I had looked at incorporating ScyllaDB into CNCF, and they're of course the cloud native code foundation, and they were asking me why I thought ScyllaDB was cloud native, and I was kind of perplexed because you literally can't run ScyllaDB without object store, which only really run in the cloud. So I guess that left me a little unsure about how to answer best this question. But in my mind, I think cloud native for me is just something that runs either only on the cloud or really nicely in the cloud. And so it integrates very easily. So I don't think things need to be like required to only depend on cloud systems in order to run. But I think it's things in which you can start to think of the software at the zone or region level rather than at the individual machine instance level, I guess is the best way that I would describe it, where the individual computer starts to matter less for the software and the collection of computers as a whole. And that could be, in a VPC, a private colo, in a public cloud. But that's to me sort of central to what it means to be cloud native.
Yeah, I might add to that a little. So my sense is what has changed is which abstractions systems are using in order to implement the things they want to implement. And so, for example, if you're running Postgres on an on-premises machine, then it's a very traditional model where it stores its data on the local disk. It treats the local disk as a block device. And it does its I/O on that local disk. And if you want any replication, then that happens at the application level, or rather at the Postgres level, sending its data to another Postgres instance on another machine. Now, you can move this whole thing into a cloud, and you could say, instead of running on local, the disk storage attached to the local instance, you could run it on something like EBS, so some kind of virtual block device. But the abstraction that it's using there is still this idea of a block device, which is still it comes from the single node hardware realization of a disk, even though it might be now virtualized and actually a cloud service underneath, because EBS is just a cloud service that provides this block device abstraction. But the shift to object stores, for example, and other and say serverless systems and so on, that's really actually using abstractions that have come from cloud services as the foundation for building things. Like an object store is not something that exists in the API of a single node operating system. It's an abstraction that has been added by cloud services. And so then, yes, that means you would normally only be able to run it on a cloud, but it's where you run it is to me less important. What's important is on top of what abstractions this system has been built, and that's really the big change in my opinion.
Yeah, thanks. I can say that I don't use the term cloud native anymore because I'm never sure what it means. But going back to what you say about abstracting, it's very interesting because both EBS and object store are new kind of abstraction, but they also provide different services. For example, both of these services are replicated by nature. So if a database that you are building on, or not just database, whatever system you build on top of it already have some replication level built into it. So my question, when I come today to design a data intensive application, maybe there are entire section I don't need to care about. Should I care about replication these days if I'm using Slate or if I'm using EBS, or maybe we can like check it as a solved problem and ignore it moving forward?
Chris, what do you think?
Yeah. So yeah, I was thinking about this actually as we were reading over the questions. I think it's a really good question, and I think the answer is yeah, you still need to care. And I think I can say firsthand, there's sort of multiple layers at which it still surfaces. The first of which is, many systems that are built on top of data layers that are replicated, they still end up needing to do replication outside of the data layer. So a concrete example of that would be, the system that I work on, ScyllaDB, is a key value store on top of object storage, but it's single writer right now. So if you want multiple writers, well, now you need to have like a sharded series of these databases, and you need to like replicate the data between them if you want some measure of transactionality between these databases, even though they're on object storage. So there's some like architectural consideration around the system you're designing, even if the underlying storage layer is replicated. I think that's even more true with something like EBS, where it's not multi-region, or block storage in general. I guess it's not generally multi-region, and so as soon as you need to have the ability to sustain a reasonable outage, you're going to need to do some form of replication. And then I think the second layer that I often see this flare up is when you're using a system that is replicated, Spanner, for example. It often appears sort of magical at first, and then you start getting really weird performance characteristics, or you start realizing that like there's caching involved and that you're not seeing the things you thought you were seeing, and it's not consistent. And so you end up kind of needing, it ends up being kind of a leaky abstraction, and you need to understand the implementation details of the system you're using, because there are fundamental trade-offs you have to make with replication, and that informs how the system's going to behave. And so oftentimes the users will get sort of a rude introductory lesson to replication through one of these systems. So I think it's still unavoidable.
Yeah, especially when you move from maybe one zone to multiple zone and multiple region, as you mentioned, you cannot really hide the latency between the regions, or you can hide it to some extent, I guess, but not completely.
Every abstraction is leaky.
Yeah, and one way that abstraction tend to leak, and to be honest, we are at ScyllaDB, we are working on it daily, is performance, and especially if you take something like object store, S3, for example, on AWS or GCP bucket, etc. Many of them present an API, but the latency that they have, for example, for one request may vary very much. So if it's local, a similar API can give you like a millisecond or 100 milliseconds. So are you consider it a fundamental different when you design a data-intensive application, or a side effect that maybe can ignore for some use cases?
I think the choice of abstraction can make a huge difference on the performance characteristics. Like coming back to the virtual block device EBS example, it's very easy to forget if you're using that every time you're accessing a block on disk, it's actually a call over the network. And every time you're doing a call over the network, it'll be fast most of the time, and occasionally the network will be congested and it'll be really slow. And so then you get this performance variability that you might have not got if you weren't making that network call, or like because it was a local disk, for example. And so I think if you then choose the abstraction in such a way that is, for example, less chatty in terms of network calls, then the system might be more resilient against network hiccups and thereby then provide more consistent, fast response times. And in order to think that through, you do have to look inside those abstractions and have an idea of what's going on. So just because EBS makes things look like a local disk doesn't mean it has the same performance characteristics that it does. And there's no quick answer to that, but I think it is important to consider those details of how it's working under the hood in order to figure out how it's going to behave in terms of performance.